So Richard is currently an assistant professor at UT San Antonio. He's also, I guess you have a joint faculty position at adjunct faculty position at Rice. Before that, he did his PhD at Stanford University with Roger Blanford, followed by a postdoc at Berkeley and another postdoc at Harvard, places you've never heard of. He's part of the Event Horizon Telescope collaboration, and his work, generally speaking, is to develop methodologies to connect the observations with the underlying computational models of accretion around black holes, which I guess is what you're going to tell us about.
Yeah, thanks, Yassine. It's good to be back here. I was in the audience for a seminar actually a few weeks ago, but now it's good to be in the podium to bring you this first population, and I say population loosely. It's yeah, I say population loosely because it's just two right now, but this is the first time that we have seen the light coming from the edge of the event horizon of a supermassive black hole, and the Event Horizon Telescope is the only instrument in the world that can do this. So the black holes themselves are, extremely interesting on their own right, but the physics of plasma in the extreme conditions of strong gravity and billions of degree heating are what I try to use GRMHD or general relativistic magnetization simulations to give us an inkling of what is actually going on around these black holes. And I've done this at many institutions with many different collaborators. So if your name isn't up here yet, it probably will be at some time in the near future. I am going to give an outline of messages that we could learn from the ability to be able to probe the horizon scale. So the methodology I use, I call observing JAB simulations or observing jet accretion flow black hole simulations. And I found that in order to have any sort of longevity in the field I am, you do need an acronym for what you're doing. So, you've probably heard, SANE simulations, MAD simulations, HARM, all of these, they really do correlate very well with lasting some time in this field. So I do observing JAB systems. The first one of these in the order in which I've investigated them is Sagittarius A star. Now you may have noticed that Sagittarius A star was not the first horizon scale image ever taken, but it was the first one that I have applied this methodology to when I was a postdoc at UC Berkeley before any black hole image was taken. So back in the circa 2018 period. And observing the JAB simulation of the Sagittarius A star entails comparing the image size and structure with the EHT constraints that existed at that time. So this is also going to be a quasi-historical tour. So you will see sometimes not exactly contemporary constraints, but with the knowledge of the time, seeing how in an agnostic way we can use this methodology in order to get conclusions that are actually predictions, and then we'll also see some of the retrodictions that come out of it as well. Designing a parametric model space that could give us insights into what's exactly going on in these in this particular source, which should be near and dear to us because it's in our own galaxy. And the next application I'm going to go through is applying observing JAB simulations to M87. So M87 has a very, very long history of being observed. If anyone remembers down to the time of Heber Curtis at the Lick Observatory around 1918, M87 back then was the first jet structure that was observed, and it has a history with very long baseline difframetry. Even a couple of decades ago, at the scale of the VLBA, 43 gigahertz, we see very nice limb-brightened images of it. So this M87 source we've seen historically through many scales, so it really may be our best studied jet. and we can see down to the horizon scale using the Event Horizon Telescope. And because we have this jet on such a wide range of scales, it's actually pretty germane to use a semi-analytic model in order to capture some of the essential properties of it. So simulations, as wonderful as they are, they really only go a tiny bit of the dynamical range of the entire system. So having a semi-analytic model where we can turn some of the knobs of the physics could actually be pretty illuminating in this case. So the particular type of physics that's we have avoided being cursed with the dimensionality of adding extra particle species like positrons in there, but the semi-analytic model makes it a very germane tool to use the knob of positrons to see if they could affect the polarized signatures we see from these sources. So they tend not to be in the simulations or the radiative transfer pipelines connect to the simulations, but in the semi-analytic models, we can see pretty stark effects of the positron physics. And we also then turn back to the general relativistic magnetohydrodynamics simulations and try to put everything together, including positrons and different type of turbulent heating and emission processes, and try to make sense of what we might be seeing in the M87 case. So the future horizons, and yes, the future horizons are just around the corner. If you ask me how long, you should really just give me some sort of sense as to what our science budget's going to be in a few years. But there are future horizons that I'm hoping.
Can't do that.
Yeah, that I'm hoping will emerge. And the Event Horizon Telescope is and its next generation GHT is on the cusp of seeing tens more.
This EHT, is it 200 gigahertz?
230 gigahertz, but it also has taken fringes at 345 for some sources.
Oh, they did went sub-millimeter.
Yeah, look at Raymond et al. A paper that came out in the past few months.
Okay.
That we have some fringes at 345. Yeah. So I know that we come from a broad range of astrophysical backgrounds here. Some of you even study astrophysical backgrounds, but I'm just going to give you a very brief rundown in mini dictionary of the soup of words that I'm going to be using. An active galactic nucleus is an emitting region thought to be around a supermassive black hole and appearing as a discrete source. The accretion disk is a inflowing, typically magnetized plasma that's bound to the central massive object. Here we're going to be using context of galaxies. Magnetically arrested disk, or MAD, is a disk whose inflow is inhibited by magnetic pressure around the black hole. Think about jamming, too many magnetic field lines in one area. You get a magnetic pressure that makes it try to bow out, so you get only a trickle of inflow in that case. And of course, we contrast that with standard normal evolution or sane. So you have that MAD and sane dichotomy. Stokes parameters are the total intensity I, the two independent linear polarizations oriented at Q and U, and a circular polarization, which is the remaining polarization. And with the Event Horizon Telescope, we have all four of these Stokes parameters information in the two sources that we've observed. And a relativistic jet is a relativistic polar outflow emanating from about 10% of AGN supermassive black holes. The leading theoretical model for these is the Blandford-Knot mechanism, in which vertical magnetic flux ends up getting close to the black hole and being frame dragged, and then you have some energy that's imparted from the magnetic energy density of the twisted field lines and processes, which I will conjecture, such as reconnection, that imparts some of that energy onto relativistic particles that can radiate. Synchrotron radiation, which is polarized radiation when relativistic charged particles gyre around field lines. So the basic phenomenon that we're going to be doing that links the astrophysical source properties to what we can see is radiative transfer. So transfer links the source properties such as emissivity to the line of sight observables like the intensity through radiative transfer equations like this one. And the radiative transfer equations are also governed by other effects. So in statistical plasma, you not only have the emissivity along the line of sight to deal with, but you also have absorption. You also have polarization, so you can do radiative transfer in all these polarized directions. Then that's influenced by each of these emissivity coefficients. It's also influenced by all of the possible absorption coefficients, and it's also influenced by the Faraday coefficients for the Faraday rotation of the linear polarization subspace here, and also Faraday conversion of linear to circular. So you have a lot of effects to do with, and you can see how numerically this can get complicated. It's not just a matter of integrating this relative transfer equation and all the effects matter. So here's where the modeling step will come in. For each of these radiative transfer coefficients, there are some properties of the population of particles that we have through the pressure of the relativistic electrons. So that feeds into the emissivity functions. So I put PE here, which can also represent the pressure of the relativistic positrons. There are also effects that have to do with the B field, including its anisotropy. Effects has to do with frequency dependence. So these effects also can be modeled using assumptions about the energy distribution of the relativistic particles parameterized by their Lorentz factor. So you can have a you can have a thermal distribution of particle energies, where the temperature of the relativistic particles like electrons governs the rate at which this exponential function gives you the amount of particles per energy. And you can have assumptions that are appropriate in some astrophysical contexts, like power law functions that govern the particle number distribution. So you can have power law tails that are governed by astrophysical processes such as shocks.
Sorry, this J is emissivity, right?
Which J? So yeah, this Ji is the. This is a pretty short pointer because it's not a laser right now. There it is. Yeah. So yeah. So this is in the simplest case of radiative transfer with just emission. This is emissivity.
Right. So
so the Ji also has
emissivity is pressure. Emissivity.
No, I mean it's not just pressure. It's this more or less. It scales like this.
No, but
It scales like pressure, but some function also of the magnetic field and the frequency. It's if you look at your Rybicki and Lightman textbook, that's what they usually teach radiative process out of. These are the main scalings that JU depends on.
But it should be some complicated dependence on the distribution function of electrons, not just pressure, right?
There is some factors, like you can put this as KE. That's one of the that's one way you can write this down. I just took out a few of the scalings. So there is
that N of gamma, that's the energy distribution of whatever your charged particles are.
I mean, right now it's a number distribution. You could add MC squared wherever you want and make it an energy distribution. Right. But yeah, basically this describes the different ways that astrophysical particles can form some sort of an energy distribution.
We are talking at 5 anyway, so we will talk about it.
Yeah, I hope this is clear.
This is clear, but I disagree, but we will continue.
Okay, there you go. All right, so the observing JAB simulations formalism can be summarized as starting with a general relativistic magnetodynamic simulation or semi-analytic model of a jet or outflow accretion flow black hole system. And then the modeling step comes where you convert the GRMHD variables to prescriptions for all these astrophysical effects. So the emission, the absorption, polarization, particle acceleration, and dissipation to emulate the sources. Then you add the observer in post-processing, and the type of targets we're talking about are, for instance, Sagittarius A* at our Galactic Center, which we've seen in 2022 with the EHT, and which we've modeled using the first paper in the series. So on the comparison of AGN with GRMHD, it's a series of papers that I've been leading. So this one was a Sean Russell in the later quarter. So we've described this process before the image came out. And then the takeaways that we actually had is that the model properties clustered in parameter space. So we had a few types of phenomenology, and all of the spectra, the variability properties, the imaging properties for each type of physics clustered in different parametric groups. And then the best fit ones happen to be a turbulent heating model that had a roughly high transitional value of the beta parameter, which is the gas to magnetic pressure ratio, at which the electrons are getting the radiation, are radiating. So only the higher beta contributions of the plasma tended to contribute to the emission in the models that work best with the observations.
So the observations, you said this was before EHT?
This paper was before this image came out, so it's a nice little check of what the methodology is.
And
So,
it was best fit of which?
Oh, no, sorry. There were observations before this image came out that had constrained the size, but that didn't look like an image. So there was radio data. So there were visibility amplitudes, there were some closure phases out there. There were preliminary proto-EHT array data out there, and that was fit to this. And the image itself, you can think of it as maybe it's a retrodiction when the image came out. So the EHT is kind of an emerging property. It's not like there's one EHT that emerged. It's kind of there are radio telescopes throughout the world that are joined together and synchronized to form a very long baseline into from a Sgr A. And some of these telescopes were there for decades. And the more and more of these telescopes, the more and more they behave like a network. And then there's not a well-defined point where the EHT existed. I mean, there may be certain grants that they won, and then you can say, oh, the EHT is now got it's funded by so and so, but mostly in Europe now. But there's not one definite time where you can say this is the EHT array. So, but we did this exercise again, but this time after the image came out for M87, and this paper actually has a lot of my group at UCSA, and this actually has Roger Blanford in here as well from Stanford. And this paper shows how the impact of positrons or electron-positron pairs can actually create a dichotomy in the two types of accretion states. So there's one accretion state that's MAD, as we talked about, magnetically rested disk, and one that's sane. And the positron effects are very prominent when you consider the different Faraday properties of the MAD and sane. So
I have a really naive question, which is, so you like this is some disk, it's presumably spinning. Like there's stuff that's in motion there.
Well, you can think of this as a magnetosphere more than a disk, though. I mean, it's a again, the sphere of magnetized plasma that's co-rotating at some frequency relative to the black hole. There's some plasma in this surely because you're getting radiation, but whether it's a thick torus or whether it looks really just like almost a force-field magnetosphere, those are different pictures that you can have phenomenologically of what's going on.
I guess what I'm wondering is like if there are features in it that are like moving at close to the speed of light, when you
the features themselves, the large scale features like these blobs, they don't move at the speed of light.
No.
The particles themselves, the particles that are generating these features.
So you don't have to worry about. I'm just thinking about like the ray
you need slow light in your radiative transfer to account for.
Sorry, what?
The slow light means that you don't approximate the speed of light as infinite when you're in radiative transfer. If that's what you're talking about, you're talking about the effects of light travel time. Yes, light travel time effects can be important. They're typically important when the bulk speed of aggregate material is close to the speed of light. That doesn't necessarily happen, it can happen. The particles themselves are almost all relativistic that are emitting at this frequency.
I guess, but you seem to be saying you don't have to worry about that here.
You need to worry about it when the bulk motion of an aggregate piece of the plasma is moving, usually at a preferable angle towards the line of sight, near that speed of light.
But the
So they
integration
call that
times
slow light.
here are like enormous. It's like weeks, months, right? The integration time to get the images.
The images, you see different days worth of data collection being represented for each of the results of the observations. So yeah, I mean,
the images that you are showing is really everything thrown.
I mean, we're close to the black hole. I mean, the light crossing time of the gravitational radius for M87 is like 9 hours. For Sagittarius A star, it's 20 seconds. So the light crossing time of each of the the individual pixels that make the simulation, it's not weights. You can get.
But are you saying if EHT actually does see some time dependence for M87?
In the papers, you look at different days, the images look a little different. Over years, they look very different. Over days, they look a little different.
I see.
All right, so let's go to the first application. So it's a setting. The setting that hopefully we're familiar with. This is our Milky Way galaxy, which is about 100 kiloparsecs in diameter. It has a dark halo with about 100 million to 400 million stars in it. And Earth is about 8 kiloparsecs from the center of this. If we go deeply into the central region, the inner parsec, we will get stars that orbit in a really eccentric fashion around what we found to be a 4 million solar mass black hole through a number of different independent ways, a couple of which got a Nobel Prize from groups led by Andrea Ghez at UTSA and Reinhard Genzel. So our question is, what happens at the innermost region of this? And that's actually a question that we can resolve with direct observation. First, by the gravity collaboration, those 4 very large infrared telescopes.
Cool. Do you want to turn off your mic on your laptop?
Yeah. So first, by those very large infrared telescopes by gravity, they found some structure, not necessarily result structure, but some infrared structure that gave polarization loops of infrared flares. And the Event Horizon Telescope afterwards, with very long baseline interferometry, gave us the first images that are resolved of the plasma in the region right around the black hole at our galactic center. So Sagittarius A star, it is between the constellations of Sagittarius and Scorpius. It's a bright non-thermal emitting region, and its distance from Earth is about 8.18 kiloparsecs, and we can know it's a percent level of precision due to the work of gravity. So even before we can take direct images, the gravity collaboration narrowed down the distance and even the mass of the galactic center source at about 4 million solar masses. What's really interesting about the galactic center black hole is its Eddington rate, its luminosity relative to the Eddington rate is very paltry. So about 10 to the minus 9 Eddington luminosity is coming from the galactic center. Models such as radiatively inefficient accretion flow give you a very, very low mass accretion rate of about 10 to the minus 7 solar masses per year. So it's a very interesting source. The source of very, very light diet, maybe a sun per 100,000 years. But you see these nice emitting regions that a number of our recent observatories I've seen. So explaining the emission processes in the low luminosity accretion region is go ahead.
The variation time of the emission it has been observed that there were some variations in seconds, right?
Well, it depends on what you mean by variation. Like if you're talking about the spectrum, are you talking about the spectrum, or are you talking about anything with structure?
No, I'm talking about the intensity variation.
The intensity variation,
The orbital time is like 20 minutes. Right?
The light crossing time of the gravitational radius of Sagittarius A star is 20 seconds. I don't understand where variability would be coming from on second timescales. I haven't heard of variability on second timescales for Sagittarius A star. But what paper are you talking about?
I mean, it was a paper last week, and I think
There was. They do see something very tiny, even on second time scale.
Okay, before I can comment on that
paper,
before I can comment on that paper, I want to see it. So you can show me the paper later. But before that, I haven't heard of second scale variation on this. But it'll be interesting. The proto-EHT arrays, whose observations date back to the aughts or the 2000s, had constrained the size of the emitting region using correlated flux density per baseline length. So this is what radio astronomers do in order to gauge size and structure. And as you can see, they were started out with some pretty big error bars and different ways to fit them. So if you assume the simplest thing, in this Nature paper in 2008 with Doloman et al., that's you just had a Gaussian shape. A Gaussian shape with emitting flux that we correlated across the globe. We see that the flux variation with baseline length gave us roughly a Gaussian that had a full width half max, implying that the size of the emitting structure was about 37 microarc seconds. That's extremely tiny. Think of tens of microarc seconds as the type of resolution you need to see an atom at arm's length, or to see, to read a newspaper in California from here. So, it's a very precise astronomical measurement to actually see structure on this scale. So when people complain about how blurry our images are, know that they're some of the sharpest images in astronomy. So with this proto-ET structure, it wasn't well constrained whether the structure was indeed some sort of 2D Gaussian, or whether it had some bumps in it. So if you have some bumps in these visibility amplitude per baseline length, that corresponds to something you can Fourier transform from the space of UV lengths, which is baseline lengths across the Earth, correlated radio flux, into the configuration space of intensity per XY space or XY dimensions in the sky. So if you Fourier transform something that looks like a Bessel function, that has this minimum over here, it looks like a ring. If you it can look like many rings if you have this structure here. So some of the updated non-point symmetric data that we were dealing with at the time that this investigation took place showed that there were hints of deviations from being a spherical Gaussian, but we started out the simplest way possible by just trying to match images with just a basic size if the image itself were just a spherical Gaussian. And we know it's not, but I'm just historically showing you how you go through this process blind and see what you come up with and seeing if it looks anything like the data. So, the final results in the intensity. So we had much better data, from our 27 observing campaign that was released in our 2022 paper, where we can actually see some large scale structures in the intensity map. And we actually did this through a number of different algorithms, and we found that with the histogram of algorithms, we had almost all of them come with a ring structure, which makes sense if you take the Fourier transform of this type of visibility data. And we did get some degenerate rings. In this case, in the lowest frequency bin of the histogram, we did get a double source. Good.
So the fact that you have multiple points stacked on top of each other is because you have multiple directions in the XY plane?
Well, the Earth also rotates, so we basically can take many measurements that are very closely related, because every time the Earth rotates, the pattern of the receivers that are looking at the source fixed on the sky changes. So we had a lot of data, and our 99% of our models converge to something that really looked like a ring with a few bright spots, and then we had a few degenerate models that are like 1%. So there's a fairly big amount of robustness in the type of results that EHT got from the astronomy side, but why don't we look at the simulation side and try to—
Can you tell me something? How come we see features which are smaller than the scattering size? You kind of take out scattering by some clever procedures, or what?
Well, what's—
Because you were saying that the
well, I mean, at 230 gigahertz, the scattering side, there's a wavelength dependence of scattering. I mean, we have some.
But on the previous slide, you said that the scattering size is like 40 microarc second.
No, the beam width. The beam width is about 20 microarc seconds. The beam width is the Raleigh criterion, basically applied to radio astronomy.
No. But what is the scattering size? Because there is a lot of scattering towards the galactic center.
The scattering size. So it turns out that among the uncertainties scattering played around as big a role as variability for Sag A star, and there is somewhat of a scattering screen that the clean algorithm had to deal with, but it's in this imaging approach, we're not using GRMHD models and putting in artificial screens. We're literally just taking the data with all the astrophysical effects, using the clean algorithm. So you have a bunch of points that you did this Fourier transform with, and you want to clean the image. You clean the image by assuming some sort of condition on where the structure is coming from, and if there were some Gaussian blurring of that structure, what the blurring would be. You remove that blurring. So we're just using the clean algorithm, and there are also some there are some maximum likelihood methods that do depend on priors in some of these algorithms, but there's no explicit here's how you account for a screen. This is just observational radio astronomy and seeing whatever results you get. There is scattering, yes. There's a lambda squared or wavelength squared effect of scattering, but all these are just taken into account with standard astrophysical imaging techniques and some algorithms that we have some sort of priors, but those priors are more based on the smoothness of the image, the sparseness of the image, maximum entropy type of images.
So scattering is taken out of the image. The actual image doesn't look like this.
The image looks like this. We're just taking the image with whatever astrophysical effects, including scattering it is, and we're using standard radio astronomy techniques.
There's no physics considerations here. It's just a pure image making.
This is the image side. Yeah, I'm gonna go.
Pure image making so far, right?
Yeah, this is pure image making.
The previous slide said that the scattering size was 40 microarc second. We see this dark spot which is smaller than 40 microarc second.
Can you see
We're not putting in any sort of model or prior or anything to take. Where are you seeing this scattering? Sorry, where are you seeing the scattering size that we're talking about?
I don't know.
No, I mean you said that what side?
Yeah, keep going.
So you said there was a slide.
Yeah,
you said the slide just before.
Yes, here. 40
Scatter,
microarc second, scattering size.
what do you mean by scattering size here?
Scattering size is the size of scatter, right? Because
It's
towards Sagittarius A star, there is a lot of scattering. At lower frequencies, you see a huge emitter because of scattering. So I'm wondering, don't they take out scattering, these radio astronomers, when they give us the image?
So even if there's a typical size of scattering effects, the relative amplitude of the scattering effects to the signal has to do with how much of an effect it has on the net effect that you see.
Okay.
So it could the amplitude of the scattering effect is also something that it could be dominated by the signal itself.
All right.
Yeah.
Back to one of the other questions you had before, in terms of the time dependence.
Yes.
These blobs these three blobs that we see.
Yep.
If we took a picture, I mean now, like would they have moved or?
Yeah. Then there are follow-up papers on the 2018 data. So this is the 2017 data, and it's taken over. Well, this is just one day, but we took it over several days. So it looks slightly different over several days, but the blobs look in completely different positions if you look over a time scale of a year. Yeah. So now let's try to investigate this from the simulation and modeling perspective. So let's take a simulation with a inflow pattern that goes between standard normal evolution and magnetically arrested disk for our fiducial simulation. We call this semi-MAD. So there's some fiducial value of a MAD parameter that is if the plasma is behaving completely as magnetically arrested disk. So this MAD parameter dealing with the amount of flux during the horizon, if it's 50 in the appropriate units, it is as if the disk completely behaves like it's magnetically arrested. But here it's 40 in the semi-MAD simulation. And we note that the dynamical timescale for Coulomb collisions between leptons and hadrons is shorter. Is is longer than the dynamical timescales of the plasma evolving. So we can roughly approximate this condition as having two temperatures, one belonging to the leptons and one belonging to the hadrons. So right now, the only emitting particles you're going to be thinking of are going to be the electrons. So this is a plasma where you're evolving the equations of magnetodynamics and general relativity, where you're considering, you have your typical mass conservation equation, but then you also have a stress energy momentum equation where you have contributions from viscosity and heating. And the entropy can be given if we take a Vlasov equation and you take moments of it, you can eventually get a equation that relates the entropy to the electron temperature. So there's a long computational way that numerically you can back out profiles like this. So you can back out the density with the magnetohydrodynamics. So you have here's the spin axis of the black hole, and you basically have a centrifugal barrier that in this outflow is squeezing out plasma. And you have a central inflow of higher density, but you have the opposite pattern with the electron temperatures. So the electron temperatures that are solved for with the entropy equation in this long numerical approach, in some of the prior simulations to the observing JAD simulations, which I'm going to show, are typically high in the funnel region and are relatively cold in the outward regions of the disk. And we went, and if we don't want to do the complicated numerics, here's where the type of observing JAD simulations second step is coming in. So we want to come out with very key properties based on a few, or even even a single parameter that parameterizes the behavior of the temperature of the radiating particles. So one type of model we could start with is the turbulent heating model that worked for a solar corona that Greg Howe's pioneered in Iowa. So this type of model has the temperature of the electrons being suppressed at high values of the plasma beta. So plasma beta is the gas over magnetic pressure ratio. But we have the higher values of the TE over the total temperature at the lower values of the plasma beta. So if we want to have this value of electron temperature without having to resort through an entropy equation and a really expensive computation of this every step of the simulation, we can just paint the simulation with this electron temperature. And the whole upshot of this is that you can compare what you get with the more expensive approach and just see if you're getting anything decent by doing this painting instead of solving this entropy equation everywhere in the simulation. So this we call the critical beta model in the paper, which I'm going to shorthand ARQ20.
So the simulation does not follow the electrons explicitly, or
the flow is given by there's one speed that's all the particles are moving in, but there's almost all, but there's a small fraction of particles that can radiate at the observed frequency. So there's a number of different energies that you could model on top of the simulation and post-processing, that you're just taking a dynamically unimportant fraction of the particle in simulations when you're doing this modeling. And you are putting that dynamically unimportant, but radiatively very important fraction into the number distribution and into the particle emission mechanism. So you are basically running a simulation according to general relativistic magnetodynamics, which numerically we can do with all those GRMHD equations. And then you're doing a post-processing step, which is a little perturbation, doesn't affect the dynamics, but that post-processing step is telling us how the fraction of particles radiating at 200 gigahertz is behaving based on some of these modeling assumptions. So
what's the intuition behind this?
Yeah, so it worked in the solar corona. So Greg Howe's had a model for this type of plasma where the plasma beta was really controlling the plasma temperature. So you can imagine with a wide variation of plasma betas in these jet accretion full black hole systems that beta might be the most important parameter describing turbulent heating physics. So there's turbulent heating, there's alpha beta turbulence, there's electromagnetic, hydromagnetic waves that go throughout these systems. There's ways that magnetic fields can interact with particles to jiggle them, to heat them effectively. And you can imagine that some sort of plasma beta is a good way to parametrically guess that the electron temperatures are going to dominate the ion temperatures at low betas, and the converse is true at the higher betas. So again, these are conjectures that we're going to test with our routine. So the next step is going to add an observer and actually see how the observations constrain what our guesses are. But that's the motivation for what we're doing. Yeah. So you can have other motivations motivated by different types of physics. So you can have the constant beta E model where there's a constant fraction of the electron, the electron pressure to magnetic pressure ratio is your parameter. And this model is a very shorthand way of showing how a process like magnetic reconnection can give you a fixed fraction of the magnetic energy and the energy of the relative particles, parameterized by beta E naught. So equipartition would be one thing that magnetic reconnection can give you between the fields and the particles, and that's with the beta E naught equals roughly 1. So there's a magnetic bias model where the pressure of the relativistic electrons could be scaled to powers of B, and this way you can actually start matching the collimation profile if the B dependence of radius scales very simply with radius. So you have a number of ways to paint these simulations, and the observations are the key test. So let's just get a snapshot of how the simulations look when you plug all these in. With the critical beta model, that exponential model that was governed above by this overall factor F and this beta critical transitional value that determines whether electrons or protons are heated, you actually see whether you are in F equals 0.1 or 0.5 or beta critical 0.1, 0.1 or 1, that they all have this intermediate boundary layer of the highest electron temperature. So this is a pretty universal behavior in this type of model, that some sort of coronal outflow is where the highest electron temperature you're going to get in this type of model is. But we have another type of behavior in the constant beta E and magnetic bias models. So there you have a roughly uniform and even brightening in the region that's at a small cylindrical radius from the jet axis in all these different types of models. But you just see some variation further away. And if you put these models in a parameter space, you can see that the models that were these coronal outflows in projection, when you add the observer in, if you add the observer going with the symmetric Gaussian size constraint, then notice that the models with the values of F and beta crit that tend to be lower had contributions from the lower beta regions that are out in the large radius funnel. But when you increase the value of F and beta crit, you start having the models conform more to the size constraint. And you can test other model families like the constant beta E model, and the high beta E model, you just see this lens profile of disk emission. So you're actually seeing behind the black hole because of the gravitational lensing. But when you tune down the beta E parameter, you actually get a small emitting region that fits the size constraint, so that's why it's green. So these very different families have some sort of degeneracy at the level of images. And you can do the same exercise with the constant, with the magnetic bias model, where n goes from 0, you have these large outflow contributions where PE goes like PB to the 0. But then when you have PE equals like PB to the 2, as you go down here, you start looking more like this lens disk profile.
So if I understand correctly, all these have the same underlying GRMHD.
Exactly. Yep.
And then you paint them differently.
Yeah. The same simulation, the same semi-mathematical simulation looks extremely different. It has extreme sensitivity to the types of underlying methods that you paint them, and only some of them look like the data.
So there must be also degeneracies between, like coming from the simulation itself, right?
Yes,
You could only change
we can talk a little bit about that. Yeah, this is a semi-MAD. We can talk about SAT and MAD. So if I get to M87, we'll definitely do a lot of this. But you can do a similar exercise with the anisotropic size constraint. So there are trends in the images when you consider the size constraint that's if there's elliptical Gaussian instead of the symmetric Gaussian. And they're basically the same trends that we saw above. The image sizes get smaller when you increase the F and beta parameters. They tend to get bigger when you increase, or sorry, when you decrease. Sorry, the images tend to get smaller when you they tend to get bigger when you increase the beta E parameter. And the magnetic bias parameter actually had a fairly weak relationship with the magnetic bias N, but you basically get the best fit models tend to have this high F and beta crit. So this is work that some students did similar work with like Elon Price in her fifth Vanderbilt master's thesis. So comparing these Sagittarius A star types of emission models, you get ways to compare with different and involving size constraints. So if you think about variability, here are the movies of different models on roughly a day in the life of each of these sources. So if you take a day in the life of each of these sources, you see that they all have levels of higher versus lower intensity, but the concentration of the intensity varies a lot depending on the model. So this is where you can see some clusters in the parameter spaces. So the type of parameter space clusters that we're giving you, these tiny crescent-shaped images that tended to fit the data the best, also have the spectra that you're getting them fitting all the different parts of the range where we had data. But the models that had the low values of F and beta crit tended to have these very large scale coronal outflows, but then you see that they have the very sharp spectrum, sharper than the data. This is when you can imagine that the temperature decreases very rapidly with radius here. And you can have a very sharp spectrum relative to these models that were mostly in the higher beta regions that are contributing to the emission.
So I thought you were going to compare these ways of painting electron to like some first principles calculation. Are you going to do that as well?
There's going to be some of that. There's going to be some of that, especially when we add positrons.
Is it just like a matter of computational power to do that, or
there is some motivation in why the ratio of Q electron over Q proton looks like it has those asymptotic values with low beta and versus high betas. So those are some of the first principles that go into some of the turbulent heating. And the reconnection, reconnection boils down to exchanging magnetic energy to particle energy. So that beta E model, even though it's pretty crude, we're going to see being used later. It's the essence of the magnetic reconnection itself is fairly simple. So there's some models that are motivated by that said reconnection, but that don't look anything like the Sagittarius A star constraints that we had when we did this exercise. And their spectra also tended to be with very large spectral excesses in high frequencies and discounted that way. The models that look more like jets with the low end constant beta E models, they might have had like a flat low frequency slope, but they also produce excess spectral emission at high frequencies. So it turns out that the best models from the size constraint, the asymmetry, the spectrum, and the morphology tended to come from this type 1. But the type 1 was degenerate, so we have a type 1A and B. So let's see if we can further break down these degeneracies. So basically, the variability is showing that the patterns move around roughly fixed envelopes of emission. So you can average these, and you can basically see that you can think of these as patterns that are moving around these envelopes. But one property of these patterns is that if you look at all of them, the one that is with this class, it barely, it might not move at all, but this one, the movie should be going, but if the movie were going, this spot would actually barely move. So it seems like this type of envelope with some variable hot region is a way that Sagittarius A star behaves. And let's see if we can compare this best type of model with the others from the standpoint of variability. So again, you take a day in the.
We're supposed to take from the spectrum that it was a good fit because it didn't really look like any of them were a good fit.
Yeah, none of them were particularly good fit, but the that there was any sort of matching of all of the regions in the space. So there's reasons why that we never expect a good fit, because there's some further non-thermal emitting electrons that we haven't modeled. So we're just modeling it as if the dominant effect is that turbulent heating process. But there are other sources of non-thermal electrons that, in order to do the investigation with testing one model at a time, the pure effect of the model is almost definitely going to be some sort of admixture of different processes. But if you can find any model that fits at least some of the points in all of the bands where there's data, that's a categorically different type of situation than where your primary emission mechanism is not fitting any part of the data, or is fitting only one part, but it's not fitting the other. So yeah, we're acknowledging that there's some extra non-thermal electrons that are probably going to be pushing this up, but we know that this is a lower bound to the type of spectra that we want. So
the upper left and lower right, the difference in the fit to the data is coming from that very high energy data point.
Well, I mean, there's also problems with having overproduction at low frequencies.
Oh, because the amplitude, your amplitude is not arbitrary.
No, the amplitude is fixed by the intensity. So we need to match the intensity in the models to the intensity of the observation. So we wanted 2.4 Jansky in our synthetic model. The problem arises where if you can fix these spectra by adding a small non-thermal population, then we consider it a good fit. If it's already producing too much in the regions that we don't want it, it's automatically very bad.
Okay.
So this is the type of constraints that we get from the spectra. So having these different classes of models, we can actually group them by their variability as well. So the type of minute scale variability that we would be able to see is only compatible with a few of these models. And there are some models, like those models that had the emitting region just sit in one spot. Those models had variability that could be precluded, and these fluctuations are extremely tiny on the time scale of a day. So it's only some of these models that had that hotspot, or that had some combination of hotspots, move around that had significant intraday variability, other than the trend line. So it turns out that even from the standpoint of variability, the models that were in the class that could be explained by existing spectral data, existing data on the image size and structure, it turns out that those are also among the models that survived in the variability. So it turns out that these models, even though you're testing a very wide parameter space, tend to form these clusters that behave the same. And among these clusters, the models that have the best behavior could be explained by the type of physics that's turbulent heating around the high beta. So this is a exercise, and we can also change the inclination, which we did in the survey. And changing the inclination, you can now see the effects of lensing. So gravitational lensing had a tremendous effect on the profiles that you saw in the above scan. But here you have a lot of this effect symmetrized by a roughly face-on orientation. So here we didn't know what the orientation was, but we can still see this trend where you get the smaller image sizes when you go to high F and beta crit. So unfortunately, you get a lot of degeneracy in the face-on images. So luckily, there was a little bit of a observer angle, but not as much as we'd expect from Sagittarius A star. So if we now have EHT and gravity together, you see that from the observing JAB simulations at 230 gigahertz, you get 230 gigahertz, you get these are how you change inclination at 230 gigahertz. And this is what happens when you change inclination at higher frequencies more relevant to gravity, if you had that resolving power. And in this simulation exercise, you see that there are some hotspots that exist in roughly face-on orientations in the infrared. You see that there are some bright features that happen at 230 gigahertz at roughly intermediate orientations. So the best style of models from our a priori investigations looked characteristically, in terms of the main image features, roughly like what you would see in the observations. Now, of course, you don't see every single hotspot mapped one-to-one here, but it's pretty interesting that from the phenomenological exercise we can get, just changing emission models in some fiducial simulations, and then seeing very, very disparate ranges of phenomenology, the type of phenomenology that fit best happened to be those intermediate observing angles with the turbulent heating model with a high value of the F and beta crit. Good.
So you showed us a few like specific values
Yeah.
parameters. In practice, do you put all this through in Monte Carlo or something? Or how?
In practice, there are students doing more dedicated investigations. At the time, this is what we were getting like a year before the image came out.
Awesome.
So yes, doing this further, it stresses that that there's a lot of phenomenological dependence on what you put into a particular simulation, and the simulation itself, it might not be the most decisive thing in what you're doing to get these images. So I'm gonna very briefly, just in 5 minutes, give a M87 version of this. So I'm gonna let you look at the EHT papers to the actual observations. The observations look like very ordered near horizon structure in M87 in polarization, also face on, but with one bright asymmetric part. So M87 looks a little bit different, and we've seen it from many different frequencies, including these 43 gigahertz edge rising frequencies, but now all the way down to the horizon. Let's try to do a similar exercise, but with the fact that we can interpret what the polarization looks like. So back in the previous exercise, we didn't have polarization. With polarization, we can actually look at the detailed magnetic field structure around, just noting that there are simple mappings between the EV or electric vector polarization angle, which is seen as ticks, and the underlying magnetic field pattern. So if your EVPA ticks look like they're radial, that means that the field is dynamically unimportant and it's just azimuthal and just goes with the flow. If your EVPAs look like either these ring symmetric or spiral symmetric EVPA features, then you have a dynamically important magnetic field. It can either be a field that's radial, which is really unphysical, or it can be a vertical field, like a poloidal field going in there. So the poloidal fields actually are consistent with the Blanford-Notchak mechanism that you saw in the cartoon above, and that actually produces a relativistic jet. So from this EVPA pattern, that tells you that there is a structure that's compatible with the Blanford-Notchak mechanism. And in the EHT simulation library, before we did observing jet simulations, we had parameter spaces that went with another turbulent heating model. This one is our beta model. It had a similar behavior in terms of beta as a critical beta model, except this one has two asymptotes. An asymptote where the ratio of ion to electron temperatures is low at low beta, and an asymptote where the ratio of ion to electron temperatures is high beta. Rather than the exponential variation with beta, as in the critical beta model, this is just this arctangent looking two asymptote model with R low and R high. So it turns out that in the parameter scan in the EHT parameter space, changing R low in the unblurred images changing R high in the unblurred images and changing R high in the blurred images doesn't really affect the morphology too much. But what affects the morphology a lot is whether the underlying simulation was spinning or not. So this is a property of simulations that have jets in them that are powered by Blanford-Notchak. The Blanford-Notchak mechanism uses the spin of the black hole to twist up magnetic field lines, and you can get this asymmetric relative beam pattern when you have a high degree of spin, like A is minus 0.94, A is 0.94, but you have roughly symmetrized versions of this when the spin is small. So these models actually tended to be a check on the MADs being preferred, actually gave some credence to the Blanford-Notchak mechanism, but there are effects that were neglected, like adding positrons to this type of polarized emission library and adding different emission models. So that's what I did. So if you wanted to make a semi-analytic model, a really simple simulation you can make a semi-analytic model of is a simulation that's conservation of mass, conservation of stress energy momentum, and it looks roughly, like this. And if we axisymmetrize this and assume parallel coefficients of radiative transfer, and we put in the critical beta model and the R beta model and compare them, we first note that the electron temperature is controlled by this beta critical parameter in the critical beta model, such that if you have a high value of beta crit, you have a slower transition in the hot electrons that can contribute to the image. So if your beta crit is high, then you basically could have the electrons being hot for longer. And that can contribute more to the emission. But in this R beta model, between two temperature ratios, you basically are controlled by your R high and R low, and you don't really have this type of flexibility. So the critical beta model has the ability to include higher temperature electrons at higher beta for a longer range of for a larger range of betas, and it can also cool exponentially at the high beta end. which can get rid of some emission.
Try to, yeah.
Yeah, so I'm just gonna show you some highlights. So let me show you some we made a semi-analytic model. The semi-analytic model showed that if you observe a semi-analytic model, the pitch angle of the magnetic field controls the emission pattern because you have a ordered and helical magnetic field pattern, and on different sides of the jet, B across n hat looks different, whereas your pitch angle changes. So that can account for some bilateral asymmetry in these images. You have a core brightened and highly polarized core, and you semi-analytic model, you can test it at different radii, but you can also add positrons to them. So adding these positrons to the radiative transfer just amounts to changing the radiative transfer coefficient in post-processing. So if we do this, then you can get some different core shifting properties for the models with positrons versus, the models with positrons versus without, have a more extended, more asymmetric, bilaterally asymmetric jet. You can compare this to some larger scale EHT images, and you can think of this type of model as being heuristically what's going on when you see bilaterally asymmetric jets in systems like A3C279. You can also put general relativity into this close to the black hole, and these models, again, they maintain their bilateral asymmetry at the level of intensity, but with positrons and without, looks very similar at total intensity. Both polarized intensity, you actually have a higher degree of linear polarization once you put the positrons in, so these scales get like twice as large. So even if a small fraction is polarized, you get very different polarization patterns. And in circular polarization, you get different structure as well as amplitude. So you can change the beta E naught parameter, and these things mix even more. So you get these more complicated mixing in that radiative transfer 4x4. And you can get a very high spectral degeneracy if you have the power law index of the underlying population change. That is effect visible only in total intensity. Well, with polarized intensity, having a spectrum where you can add positrons has a very, very sharp decline in the Stokes V, only with the models that have a lot of positrons that can't Faraday convert. So I'm going to show you the comparison I want you to see the most is between these simulations, the MAD and the SANE. So if you have a MAD simulation, you put in positrons, the V over I decreases structurally linearly in the positron fraction. If you have a SANE simulation and then you put in positrons, the EVPA pattern changes wildly by adding even just 2% level different positrons from frame to frame. And this is because the Faraday thickness of the SANE simulation to have the same flux as the MAD has to be much thicker. The density has to be much thicker. So adding positrons to a SANE flow has a very rapidly time-dependent intensity with EVPA pattern, and it doesn't exhibit the monotonic decrease in V over I. The monotonic decrease in V over I is coming from the fact that in some of the SANE slices, you have intrinsic polarization giving the whole thing. And that intrinsic polarization with the adding to positrons, the positrons cancel out the intrinsic circular polarization in the frames that have domination by intrinsic circular polarization that we found that happens during flux eruption events. So this is what my student Helios is doing. And you can see this is a slice of the flux eruption event. And that's where you see that linear monotonic decrease in V over I when you add positrons. And you don't see that for any of the SANEs. And yeah, so future directions, you can, I would have talked about axions and how you can try to find an axion profile modulating the EVPAs. And you can compare that with the astrophysical compounds that we found with the EVPA rotations that we saw when we had positrons. So I'm gonna let thank you for all the good questions in the very early part of my talk.
Thank you very much. I guess we can ask you more about the rest of the video.
Yeah, thanks. Oh, you can ask questions.
Yeah, I missed where the positrons. I'm not familiar with this area.
Yeah.
So where do the positrons?
Yeah, so that's a good question.
Why are there so many positrons?
Yeah. So there are only positrons in the very large M87 AGN and not very many positrons in the Sagittarius A star case. And these positrons are coming from the Bright-Wheeler gamma-gamma type of interactions that you have when you collide.
Oh yeah, this one.
Yeah. So if you have soft photons of low energy and Comptonized photons, then you could end up having energetic gamma-gamma interactions that have enough energy to create Bright-Wheeler pairs on the funnel of the jet. But you can also have spark gap processes where you have.
But go ahead.
You can also have processes where there's very little plasma between inflowing plasma to the black hole and centrifugally outflowing plasma in a jet. And in this unscreened electric field, you can have particle cascades that are creating electron-positron pairs. So there are two sources, but they really only are significant for the large AGN M87. The spark gap processes are not too important for Sagittarius A star. So that's why we put the positrons in the model for Sagittarius A star, not in M87.
Thanks.
Okay, thank you, Richard. You're here until end of the day today and
Yeah.
tomorrow as well, or not?
Oh, no, I'm leaving tomorrow morning.
Okay.
But I have meetings with some of you guys.
Yep.
All right, so
Okay,
thank you.
yeah.
Thank you very much.